Hello everyone. Today we will discuss one of the topic in cryptography, and what we will discuss is one of the standardized hash function in cryptography, which is called SHA 512. Okay, before we go to SHA 512, we would like to know what hash function is. This is probably similar to what the definition of hash function in database. So here, the hash function will map a message with variable length to a fixed hash value. The hash value is called message digest. So in this case, the input is a block of data M with variable length, while the output is the hash value with fixed length. So this is the function, the hash function. It will map M here, message, to H. In this case, H is the message digest hash value. Okay, and similar to database or algorithm, the property of good hash function is like this. So the function here should produce the values which are evenly distributed and looks random. If we have, for example, 8 bits of hash value, then the number of possible value is 156, and each of the value should have the probability to appear 1 over 256. So the probability of the occurrence of each hash value should be roughly the same. The main purpose of hash function here is for data integrity. It means that the receiver will know if the data is modified during the transmission. It cannot prevent modification to the data, but at least when the data is modified, then the receiver will be able to identify the modification. Since the main purpose of hash function is data integrity, then changes to bits of M, any bit, just one bit, should produce random changes in hash code. So even though there is only one modification, for example, one bit 0 becomes 1, is changed to 1, but the hash code that is produced should be very different from the original hash code. And the hash function that is needed for security application is referred to as cryptographic hash function. So what we will discuss later on is cryptographic hash function, and we will focus on one of the cryptographic hash function, which is SHA 512. In cryptography, there are several applications of cryptographic hash function. The first one is for message authentication. So in this case, what we want to do is to verify the integrity of the messages, like what I already said previously. If the hash function is used to provide message authentication, then the value of the hash function is referred to as message digest. The second one is the use in digital signature. So in this case, the hash code will be encrypted using the sender's private key, The receiver can decrypt the hash code using the sender's public key. So in this case, it is guaranteed that the original hash value is encrypted using the private key of the sender. So it means that it is the sender who encrypt the hash value or who send the message. Any attacker who wants to modify the message must know the sender's private key. Yeah? But since it is private, then it will be impossible for an attacker to modify the message then. Now we will discuss the standardized hash function. The name is secure hash function. There are several versions of hash function. Originally, it was published in 1993, built by NIST, and the algorithm is based on message stages 4, MT4. In 1995, the revised version was released, which is referred to as SHA-1. The original SHA is now referred to as SHA-0. SHA-1 produces 160-bit hash value. In 2002, NIST built a new version of SHA, and it is referred to as SHA-2. There are several variations of SHA-2, starting from SHA-224, SHA-256, SHA-384, and SHA-512. The number here indicates the length of the hash value. So SHA-224 will produce hash value of 224 bits, while SHA-512 will produce the hash value of 512 bits. This is the comparison of SHA versions. This is SHA-1 and these are SHA-2. The size of the message stages is different between them, and then the message size are also different. SHA-256, 224, and SHA-1. The maximum size is 2 to the power of 64 minus 1, while SHA-384 and 512, the maximum size is 2 to the power of 128 minus 1. And then the block size is also different. Means that the word size is also different. And the number of steps also different. And the security level here actually based on the work factor related to birthday attack in message digest with size n. The word factor for message digest with size n, then the work factor is about 2 to the power of n divided by 2, which is based on birthday paradox. Okay, now we will discuss in detail SHA-512. The maximum length of the message is less than this one, so it is 2 to the power of 128 minus 1 bit. And then the output consists of 512 bit message stages. This is a kind of block processing. So the input will be processed, and the size of each block is 1024 bit. Yeah, this is the illustration of message digest generation using SHA 512. Yeah, as we can see here, the message is divided into blocks. Then the size of the block is 1024 bit. For the last block, we need to add padding. The padding is mandatory. So the padding consists of 1 and then followed by zeros. The last 128 bit in the last block is used to indicate the length of the original message here. The length of the original message. And then each block will be processed using function f. And then it will be applied with additional operation with IV for this one, or with previous hash code for this one. So basically, this is the addition operation here is applied to the result of function f, with the previous the hash code of the previous block. But since the first block doesn't have previous block, so we have here IV. And then the last code here, the last hash code, or the hash code produced for the last block, will be the hash code, the final hash code. So as you can see here, we have a kind of chaining between the hash code of different blocks. Yeah, okay, we will go to the algorithm now. Step 1, as you can see in the illustration, we need to add padding bits. So the message length here must be congruent modulo with 896 modulo 1024. Why it's not zeros? Why it's not 0 modulo 1024? Because we need to put the last 128 bit here to indicate the length of the message. So that's reserved. Yeah, and padding is mandatory. It's always done, even though the message length is already meet the requirement here. That's why the number of bits to be padded is between 1 to 1024. Okay, and the padding consists of single 1 bit followed by 0 bits. Okay, then the second step is add a block. The block here consists of 128 bits, so it is not a full block which consists of 1024 bit, but it is additional block here to fulfill the length here for the last block. So add block here is this one actually. The one that's added is the 128 bits to indicate the length of the message, the length of the original message. Okay, so now we will have n times 1024 bits, consists of m1, m2 to mn. After that, we do hash buffer initialization. So to calculate the function here, actually we will use 512-bit buffer to store the temporary and final hash code. The buffer here is represented as 8 64-bit register from A to H. A, B, C, D, E, F, G, H. And the initial value for each of the 64-bit register has been defined here. So A, this is the original A, the original value of A, B, C, D, E, F, G, and H. Okay. Now step 4. Step 4. We process the messages in 124-bit block. Yeah, so we process the message block by block. For this one, we need to make use of the function. Function here consists of 80 rounds. Then the input of each round is the buffer itself from A to H. Then in each round, the value of buffer is updated according to the rules in the function, defined in the function. Input for the first round is this one, buffer value HI minus 1, the initial value of the buffer. And then in each round T uses 64-bit value WT. WT is derived from the message in the block, message in the current block, in the block that is being processed, which is MI. And then each round uses additive constant KT. This is already defined as well. So this has been standardized. And then output in round 80 is added to the input of the first round to obtain HI. The addition here is independently performed for each 8 words in the buffer with the corresponding word of HI minus 1 using modulo 2 to the power of 60 addition. Yeah, so addition here is performed in this modulo 2064. Yeah, and this is the last step, the output. The output here is the nth hash function. The nth hash function. So that will become the 512 message digits. Yeah. This is the illustration of block processing. Illustration of block processing from round 0 to round 79. So here we have W0, W1, 2, WT, W79. This is derived from the message that is currently being processed. The input of each round is the buffer, and also KI or KT, K0, KT, K79. In the last round here, we need to add the value of the buffer here with the original, with the hash code of the previous block, like this. That will be HI. HI here is the hash code to the to block number I. So this is not the final hash code. This is only the hash code in that block, for that block. The hash code for that block. While the final hash code will be obtained here. So after everything is processed, after every block is processed, then the hash code of the final block will be the final hash code here. Okay. Yeah, now the round function, the one that is complicated. Each round is defined like this. So actually we have here the same operation for each round. first we need to define T1 and then T2. Yeah? T1 is defined as this one, H is buffer H, and then C, H, E, F, G here is defined like this. Yeah? E and F, SOR, not E and G. E, F, G are buffers. And then followed by this one, and the definition of this one is already defined as well, like this. So it is n-bit circular right shift. In this case, we have 14 bit circular right shift rotation of 64 bit arguments x of e, and then SOR with again circular right shift, but in this case, in the second element here, we have 18 bit circular right shift, yeah, and then the last one here, 41 bit of circular right shift. Yeah, so that's this one. Then WT is the current word derived from the block that is being processed now. Yeah, and then we also have KT here. KT here is the additive constant, which is already defined. I mean, it is already standardized. Plus here is modulo addition operation, but applied to modulo 2 to the power of 64. So addition here is addition, not SOR operation. T2 is defined like this. This is the definition, similar to this one, I think. And then match ABC here is a kind of maturity. So A and P, SOR A and C, SOR P and C. It produces true if the maturity or 2 or 3 of the arguments are right. 1. Okay, and after calculating T1 and T2, now we need to update the buffer. So G, F, and E are a kind of shifted here. So E now is located in F, F is located in G is located in H. This is also similar to C, P, and A. The one that must be updated, not just shifted, is E. E here is T plus T1. T1 is this one. And then A is T1 plus T2. T1 here plus T2. Okay, so 6 of 8 word output in round function are rotation, like what I already mentioned. P is located in C is located. P here is located now in C. Yeah. A is located in P. C is located in T, yeah, and so on. Two other words, two of the buffer A and E, are generated from substitutions from the operation T1 and T2. What about word values? Word values WT. So in this case, we have 64-bit word values, yeah, for each round, and it is derived from the current block. The first 60 values of WT are taken directly from the 16 words of the current block, while the remaining values are defined as follows here. So WT is this one, WT minus 2, with this definition. This is the definition of A0512X, n-bit circular right shift. In this case, we have 1-bit circular right shift, then 8-bit circular right shift, yeah, and left shift, just left shift, not circular right left shift, yeah, of WT minus 2, yeah. And then WT minus 7, and then plus this one times WT minus 15 plus WT minus 16. Yeah, this is the word values for the words other than the first 16 values. Okay, until the 80 round number 79 has been, until around number 79 finished. Okay, that's the word values or WT. Okay, and these are SHA 512 aspects. So in SHA 512, each bit in the code is the function of each input bit. Then complex iterations of function f produces a value that is mixed well. So if we choose two messages randomly, even though they have similar regularity, the hash code that is produced from two messages will be different, and we cannot we cannot infer the pattern between the two messages. So they look very random. And then in terms of security, here the level of difficulty to produce two messages with the same message stages is this one, 2 to the power of n divided by 2. And here is 512, so 2 to the power of 256 operations. The level of difficulty to produce a message with a given message stages is this one, 2 to the power of 512 operation. Okay, yeah, I think that's SHA 512. This is the book from which the slides are obtained. Yeah, and that's it. Thank you for watching this video. We will meet again with the discussion of other topic in cryptography next time.